Alright, hello and welcome to discussion 3. I'm going to start with a pun of the day because someone put this in the slides and I think it's funny. I heard a beautiful guitar solo and started tearing up. Guess the music. Struck a chord! Okay, on to some logistics. Project 1 was released. The checkpoint quiz, that was due Tuesday. That's already passed. And the write-up in code is due February 16th. That's this upcoming Tuesday. And we have some project parties scheduled. You can check Piazza for the dates, but if you're having trouble, then come to one of those. Okay, so in lecture, we went over some different ways to represent geometry. We first talked about implicit representations. So these are defined by some sort of equation or relationship. For example, say you have a function, like a function of a sphere, and you just define your object to be all points which satisfy your function equaling 0. The pro of this is that you can do these very simple inside-outside tests, since you would just feed your point into the argument of the function, and you can perform intersection tests easily, and this is quite compact, since all you really need to store is this function. The cons of this are that it's hard to sample, and it's hard to model complex shapes. So you can imagine having some sort of figure of a person. It's not quite clear what function you would need in order to actually represent that person in an implicit way. So we also have explicit representations. So this is where you store your points directly. So you could imagine just having a list of points, and that would fully describe your object. It's easy to sample these since you have, like in a list or some sort of data structure, you have all the points that are part of your object. It's easier to represent more complex shapes since you can just define these points in whatever way you want. And the cons of this are that it's harder to test whether you're inside or outside an object, and they require more complicated data structures to actually store this list of points and make this list of points understandable to your program or to other users. So we will talk more about that in future lectures. Okay, and so the second thing that we talked about this week were splines. These are essentially curves or polynomials, and we can define these in a couple of different ways. The first way to actually create this polynomial and define this polynomial is through cubic Hermite interpolation. So what we need in order to define our curve in this way are 2 points, the start and the end of your curve, and the first derivative at your first point and the first derivative at your second point. So that would give you 4 points in total, and that means that the output would be a cubic polynomial that is interpolated between these 2 points. And now I'll just go over the derivation of this. Okay, so probably the most common way you have seen a polynomial being represented is using these basis functions over on the left here. So you have some coefficient, t3, some coefficient, t to the 2, some coefficient, t, and then some value. And in order to get to this representation from these 4 points that we've defined, we need to multiply these 4 points by these basis functions, in order to recreate our polynomial.